Good morning, everyone. It's a special pleasure for me to introduce our guest speaker today, Professor Dr. Fabian Beck from the University of Duisburg-Essen in Germany. Fabian Beck is an assistant professor, and he is leading the research group on software visualization. And as we have discussed before the Christmas break, software visualization is one of the ways to analyze the rich data we can collect in the software engineering context. So without further ado, Fabian, the stage is yours.
Thank you. Good morning, everyone. Happy New Year. Thanks for the invitation today. I want to talk a bit about visualizing software dynamics, which is a subtopic of software visualization. Yeah, like Alexander already said, I'm working at the University of Duisburg-Essen as an assistant professor, and we are doing a lot of software visualization, but also a bit broader information visualization and visual analytics. Maybe a brief explanation what this is. Information visualization generally deals with the visual representation of abstract information. Software visualization is kind of a sub-branch of information visualization, basically applied to data from software engineering. And there's also visual analytics, which looks at visualization at a broader perspective, kind of. It also includes aspects like human-computer interaction, but also how to connect the visualizations with machine learning approaches and artificial intelligence. So there we discuss like bigger analytics system that have a visual component, but where other parts also play a certain role. And this is, of course, also applicable to software engineering data. So my background is originally in software engineering. So my PhD at University of Trier I did in the area of software engineering, and so that's also why I know Alexander and other folks from the software engineering community. I studied software evolution, code coupling, code comprehension, modularization, and different architectural patterns in my PhD research, and then I moved to a visualization group where I kind of generalized the visualization methods that I was already using before in my PhD time to other application areas, and yeah, worked on general visualization approaches. So software visualization nicely combines the two areas. This application area of software engineering and the methods from visualization. What I want to talk about here is a bit a direction going in with respect to performance engineering and dynamic analysis. So specific applications of software visualization on data that is collected during, or that has a dynamic component that is collected during the execution or during the evolution of a software system. So I'm moving in that direction. And this talk today is kind of a bit of a personal research perspective on these areas. So I will show some works that I did in the past with colleagues. But please be aware that of course, there are also other works. I will also reference a few of them, but if you're interested in more details, you can always look up the related work sections of our papers. So today, this is more a personal perspective, basically, on visualizing software dynamics. So I like to start with a maybe controversial statement, I'm not sure. By the way, if you have any questions, just interrupt me or mention it in the chat. I think it makes sense to directly address them and not wait until the end of the whole thing, because we're covering a lot of different topics. So if you have a specific question, just go ahead and we can directly discuss it. So my controversial statement, software is invisible. So you can't directly see the software. I mean, yes, there is the source code. So this is kind of the only natural representation that software has. You can look at the source code of the system and basically see what it does, but in practice, that's not really possible for the whole system, because even a system with middle level of complexity, nobody can read the full source code anymore. These are 10,000, 100,000 of lines of code. So nobody can be aware of the whole source code of a system. You can also say, yeah, you can maybe look at the front end, but not every software has a front end, plus not everything that happens in a software system is directly reflected in a front end. So this is only kind of the tip of the iceberg, if you like. So, but the main thing, the main software is basically invisible. So software visualization deals with this problem, and visualization can help make software visible on different levels of abstraction. So software visualization in general is nicely covered in this textbook by Stefan Diehl. It's already a couple of years old, but still gives a good overview of what different kinds of data you can analyze regarding software engineering, and what insights you can gain from this. So I'm referring here to this textbook. If you're more interested, what I want to take from this textbook are two definitions of software visualization and briefly discuss them. And these definitions also help kind of to explain what is the focus of this talk today. So one definition is software visualization is about visualizing the artifacts related to software and its development process. And as we will see also in the following, what is considered an artifact here can be very different things. So it can be the source code, but it can be also information about the execution of the software, or information about the process and the people involved in this process, for instance, the software developers. So artifacts is a broad term here that is intentionally picked to cover all these different aspects of data that stems from the software development process. Another definition is that software visualization is about visualizing the structure, behavior, and evolution of software. So the structure relates to, for instance, the architecture of the system, and there's a lot of research already on this. What is very interesting regarding the behavior and evolution is that these two things have a temporal component, and this makes it specifically challenging to analyze and interesting for research with respect to visualization also. So behavior and evolution are the two things we want to focus today here in the area of software visualization. So that's what I refer to here as software dynamics. On the one hand, you have the evolution of the software. You can use the metaphor here actually of the evolution of species. So from a very simple species at the beginning, the software evolves into a more and more complex system, adapting to its environment, acquiring new features, and so on and so forth. So that's one of the dynamic dimensions I'm referring to here. But there's also a second one, which in this metaphor can be the life of an individual of a species. So the software gets executed, so it lives for a certain time, and then it stopped because the job is done, and that's basically the life of an instance of the software system, a bit like the life of an individual of a species. It doesn't become a different system in that lifespan, but the data that is processed is changing, so it goes through different states and kind of, if you like, collect some experience in this lifetime. So these are two temporal dimensions that I want to discuss today. First, visualizing software evolution in the first chapter. I think that's what we will cover before the break. And then in the second and third section, in the second section, visualizing software execution. And then the third section combines the two, visualizing the evolution of executions. Finally, I will conclude with some challenges with respect to these visualization topics. So let's start with the software evolution and its visualization. Like I said, various researchers have worked in this area already, and in general, maybe first let's clarify what software evolution refers to. And there I want to quote an influential article by Frederick Brooks, No Silver Bullet, from '87. The quote starts with, "All successful software gets changed." So it's the observation that software is maybe not like a bridge or so that is built and then stays there. Maybe it's maintained a little, that it doesn't fall apart, and at some point it just gets replaced by a new version of the bridge. But software gradually changes over time. So there are new releases and bug fixes and so on and so forth. This might be a very natural thing for you, but in '87 it was maybe an important observation, because people tend maybe to build software systems like bridges, or try to do this at least. But here the explanation is why this happens, that this is different here. Maybe I can read the quote. Two processes are at work. First, as a software product is found to be useful, people try it in new cases at the edge of or beyond the original domain. The pressures for extended function come chiefly from users who like the basic function and invent new uses for it. Second, successful software survives beyond the normal life of the machine vehicle for which it is first written. If not new computers, then at least new disks, new displays, new printers come along, and the software must be conformed to its new vehicles of opportunity. In short, the software product is embedded in a cultural matrix of applications, users, laws, and machine vehicles. These all change continually, and the changes inexorably force change upon the software product. So we observe this evolution of software. So I have a question for you, actually. Maybe we can collect some ideas briefly through the chat. What are relevant questions that software developers can answer with data that stems somehow from the evolution of software? I'm not sure what exact topics you have covered in this lecture series already. Maybe some of that applies here, maybe not, I'm not sure. But I would be interested what ideas you have when you hear the term software evolution, and what you can learn as a software developer from software evolution, or data that is collected or somehow relates to the evolution of software. So maybe just post some ideas in the chat. Give you a few minutes, a minute or two for this. In the meantime, I was able, I think, to solve my camera issue. So hopefully you see me now. Hi. Any suggestions for my questions?
Yes, we can see you now, Fabian.
Great.
Well, some of you have attended the course on software evolution last year, so they might like to contribute to this discussion. And those of you who have not, I wholeheartedly recommend the course, which will start in February, in Q3. And this year, Dr. Eleni Constantino is going to teach it.
Sounds like a very interesting course. Yeah, maybe it's not super obvious, because it's maybe those questions are more implicit. So it's not like, yeah, I have a specific problem and through software evolution I can directly solve it, but it's maybe more that, I don't know, for instance, you have a bug in the software and you need to find, or maybe it's helpful to find out when this bug was introduced. So this might not directly solve the bug, but it might give you some important information. Maybe you can also talk to the person who wrote this original code. That's just one suggestion for this. I'm not sure, so nobody's typing, so maybe we can leave this open a bit and come to this back later when you've seen some visualization approaches. Maybe a general comment on visualization is also visualization is not directly answering specific questions, but usually a good visualization can answer many questions. Some of these questions, maybe even the developers of the visualization did not really think about it. So unlike a, let's say, a machine learning approach that answers a specific question or some other algorithmic solution that solves a very specific problem and gives a clear answer, visualization does not give these clear answers, but it just shows you the data, and it's up to you what you can read from this. So you can solve different analysis tasks, usually with one visualization. Okay. Let's see some visualizations then. Like I said, others have worked on visualizations in this area for quite some time. So one of the very early software visualization actually visualizes software evolution. It's called an approach called CSoft that you see on the left side. It's very close to the code. It visualizes every line of the code in a different color. And you can encode different metrics in the color. For instance, who wrote this code or how old the specific line of code is. So you can choose different metrics here. Some of them relate to the software evolution. And the nice thing about the system is it also gives an overview because you're able to kind of zoom out and use these kind of thumbnail representations and even beyond, even more compacted versions that summarize a metric with respect to a certain code file. Then in the middle, you see another approach that deals with different kind of software metrics and how they evolve over time. So you have, for instance, complexity metric. The complexity of the software changes over time. You can, for instance, observe if your system gets more and more complex, or, for instance, if you do some refactoring efforts, if you can decrease the complexity of your code over time. So this is represented here. I'm not sure you see my mouse pointer. Probably not, I think. See. Now you should see it. So every of these radar charts here are keyword diagrams. They have different names. Shows a bunch of different metrics, so maybe about 12 or 15 different metrics. So every of these lines is a different dimension of a metric, and then you use a line connecting the different dimensions here for one version of the software. So every version of a software creates such a line, and then you have different lines for different versions, and then the color coding is used to discern. I'm not sure exactly the color legend is missing here. Let's say red is the newer versions and blue are the older versions. So you see that some metrics are growing here, for instance, while others stay very constant. One radar chart describes one module of the software system. You see different modules, and you see quite different changes. So some module only have very limited changes with respect to the metrics, while this module in the middle undergoes quite big changes. There also see some connections between the module that kind of reflect the architecture of the system. And then we have here on the right-hand side code flows, which shows also a bit like CSoft. We are talking about the code level here. So this is basically a summary of all the code of a system or part of the code of the system. And the indentation here, or this hierarchical structure here, shows basically the indentation of the code and then how it was changed over time. This piece of code was not growing, so it's maybe an exceptional case. Often code is growing. And you see some changes happening here, that something is moved from here to the bottom, and stuff like this. So every column here is a different version of the code, and you can see how it evolves over time. So this gives a general overview of what you can do, and now I'm present a few of my works and give some insights that I learned doing these works, basically. So I started to look at the dependencies of a software system. And so the dependencies basically explain the architecture of a system, or one important aspect of the system's architecture. And if you study that over time, you get quite challenging data set, because software systems aren't like small. You have hundreds of different dependencies. So what we visualize here is each version in one column, a bit like in code flows, but now it's not showing the code itself, but the dependencies that are contained in the code. So every line you see here relates to a dependency. If you would do that in a standard node link diagram, where every class would be like a circle and every dependency between two classes would be a line between them, you can also do that, but this doesn't scale beyond, let's say, 50 different classes. So, but software systems are usually bigger. This is maybe a small to mid-sized software system. JUnit, so you might know the system. It's a testing framework for Java. This is not particularly big, but already contains a couple of hundred classes, and even more dependencies, of course. So visualizing this as a node link diagram would maybe work for a single version if you select a subsystem, but what about the whole system, and what about showing the evolution? So our goal here was to come up really with a scalable visualization solution. So we use these columns for every version, like I said, and now every line from left to right is a dependency. You have here on the left the structure of the system. So if a line goes from here to there, it connects some class from the UI package with something from this framework package over here. And instead of showing the lines directly, we show line density here that allows us to see some structure even in very dense areas that we have here, for instance. If you would switch this feature off, you would just see less structure in these dense areas, basically. And you now see like the big changes that happen in the evolution of the system. You have here the version numbers. So one big change is between version 3.0 and 3.2, or between 3.8.2 and 4.0. You see bigger changes in the system. You can now explore the system, basically zoom in and find out exactly what are the specific patterns here. You see different kinds of patterns, for instance, like this directional thing here, this directional link from the UI package to the framework package. But you also see some more like hourglass patterns that go in both directions. That is okay, like this one here. That is okay within a package. That's called high cohesion of a package or module, but you don't want to have this between different packages. Then it would be high coupling. That is something you don't want to have. So maybe you know this recommendation of high cohesion and low coupling. Yeah, so you can see the big changes, but you can also explore these patterns in the evolution here. So an observation from this approach is that changes of the low-level structures provide first insights into the evolution of the system, and it shows the big changes in the system, basically summarize nicely the history of the system. But one problem of this visualization is you see that the system changed a lot. We are looking at a large time span here, many versions, and you see that the final version is quite different from the first version, but they still share the same package structure here. So what we had to do here is kind of collect all the packages that at some point were introduced and aggregate them in this package structure. But this is not the final package structure of the final version, and it's quite different from the first package structure. So this is kind of an artificial construct that we have here on the left side. What about if we also want to visualize these changes in the hierarchical structure of the system? So in another approach, we focused more on this. It's not as scalable with respect to how many versions we can display. And so here we show only 4 versions of the system. So we summarize some of the JUnit versions, still the same data here, but a bit more summarized regarding the different versions. And now we chose a very different metaphor of representing the dependencies in the system. So here we visualize the dependencies as an adjacency matrix. So it's still a network or graph structure, but instead of drawing lines between the entities, we use a matrix where the code entities, the classes of the software system, are the columns and rows of this matrix, and we draw basically one of these small rectangles here in the cells if there is a connection between 2 of the classes. Those classes are again hierarchically organized, which is shown here at the side of these adjacency matrices, and now we can represent the changes in this hierarchical structure. So we see like the very stable packages, like the gray ones here, or stuff that changed a lot, like this class here. So the other classes were kind of discarded, and new classes were introduced in this package. Only one remains the same. You see also the bigger changes later on here, for instance. So if we look into the adjacency matrix, now we observe certain clusters along the diagonal, which is very typical for a software system. It relates again to this principle of low coupling and high cohesion. You have the high cohesion inside the packages, many dependencies inside the packages, so you get a lot of those rectangles inside, or these marks inside these rectangles on the diagonal, with some exceptions like this one here. This is a strange case. The more marks we have here, we also use the background color here. The darker the background color gets. And then we have some dependencies between the packages also that you can see here, for instance. So this package is connected to all the other packages. This is maybe also some interesting observation. Now going through the versions, we see that this pattern pretty much remains stable here. It gets extended here, but still the same somehow. And then in these changes here, then the system gets very different, and it's maybe not as long, like has this clear structure that we observe here. We have here a lot of white space, which is good probably, and here the system got more complicated. We don't see these big white space areas anymore. So judging if this modularization of the system is still good or still nicely reflecting the dependencies, we also did a software clustering here. So we took the dependencies and let a clustering algorithm decide which ones are good packages with respect to this principle of low coupling and high cohesion. So the clustering algorithm tries to put those classes in the same package that share a lot of dependencies. And so that's what we display here. It's still the same dependencies, but organized differently in a different hierarchical fashion. And then we can compare the clustering result with the original package structure in the first versions, in the second series of versions, and so on. So here we see only small differences. So the original package structure is close to what a software clustering algorithm would automatically compute based on the dependencies. So this seems a very obvious and good solution. And the more complex the system gets, we also see bigger variations. So if you compare compare, for instance, this is adjacency matrix here with this one here, you see that the algorithm was able to produce a much cleaner result than a bit this messy, more messy looking like adjacency matrix down here. So this could give some inspiration or could explain how the system developed, maybe also provide some historical context why certain things look like this, because they originate from maybe a different package, and it makes suggestion how you can maybe improve the modularization of the system in the future. By the way, you might have noted the picture on the first slide. This is a 3D print of this particular visualization that we once did, just for fun. An observation here is that also the high-level structure of the system, not just the low-level code and the code dependencies, but also the modularization of the system changes quite a bit through the versions, and that is something that is maybe important to understand if you want to understand and improve the current modularization and structure of a system. So these visualizations give you kind of an overview of the evolution, but in your everyday work as a developer, you might not always want to go back and study the whole evolution of the system. That's maybe nice at the beginning, or sometimes nice to look back at the whole history, but in practice, you work in the code editor a lot, but the problem there is you don't have any information from software evolution. So some information that might be helpful, we tried to include in the code editor itself. So we experimented with visualizations that can be directly put into the code editor, and this is kind of an example. So we have here a method declaration close all buffers, and we attach this visualization here that stems from data of the software evolution. Okay, so this visualization is not very rich at the moment, but you can hover that and then get an explanation what this visualization actually means. It summarizes the evolution of this specific methods in the code. You see here the change history of this method, so all the commits that somehow changed this method, and you see that in the last 7 days there was no change, in the last 4 weeks also not, and then we had the last 12 months we had a few changes, and then also earlier ones. This is actually summarized here in this little timeline representation. So the large box at the end represents the last 7 days, then we have the last 4 weeks, last 12 months, and earlier. The idea here is that actually for a software developer, often the recent history is much more important than the very old history, because, for instance, if we talk about fixing a bug, it's much more likely that it was introduced recently than it was there for years already and nobody noticed. This can happen, of course, but more bugs, more bug reports from recent changes, of course. Another aspect that is covered here is code change methods. So that's also very interesting information from the software evolution. So if you want to change this method, you might also need to change other methods. So often, if you, for instance, want to fix the bug or extend a certain feature of a code of the software, it's not local in one method, but you have to change several methods to implement the respective thing. So we can learn from the history of the changes made, actually, which are the methods that often change together. So, for instance, you have a very similar method elsewhere in the system. So if you fix the bug in this method, it might be also included still in the other version of this method. Of course, you try to avoid code clones so that you don't have the same code over and over again in the system. But in practice, it often happens that there are code clones, or at least code that is very similar and does very similar things. So if you extend this feature or fix a bug in this feature, you might need to look at both. Or due to technical reasons, it's important that the functionality is distributed across several files, and you need to change all the files, all the different methods. So that's a way how you can use software evolution in practice in the code editor itself in your everyday work. So recent history is often an important context when you work with the code. Finally, as a fourth approach, I want to cover a bit of a different aspect, which are the software developers. So far we focused more on the technical dependencies and specific changes made in the code, but you can also ask questions about who worked on the code, who's the expert with respect to certain features. So you can just ask the person for some advice if you want to implement a feature relating to this part of the code. So we developed a visualization that shows the evolution of a software system regarding the developers. Here we see the Linux system and 5 important modules of the system. So these are the file system, network, architecture, kernel, and drivers. So this is very high level, but we can see and get from the Git repositories who worked on which parts of the Linux system. So if we count basically how often they committed with respect to these different modules, we get different kinds of developers. Some of the developers have worked on all 5 modules. This is shown in this line here. Or some have only worked on the file system, which is shown here. So these different rows here indicate these different kind of intersections of contributors, or different intersections of modules and contributors who worked on these. We sorted them here by stability. So the most stable, where the combinations where the contributors are most stable are at the top. So it's very interesting to observe that this combination of all 5 modules, that basically contains all the main developers of the Linux systems who are familiar with all parts of the system and not just occasionally contribute some of the parts. They stayed very stable over like a decade. So this is shown here in this line. So every developer is basically a line here, and if a line moves, then the developer, like for instance from here to down here, moved from editing all 5 modules here to only 4 in the next year, and then maybe back to all 5 in the next year. So you can follow the different developers through those lines, or you can look where are the stable lines, and this is a specifically interesting case. Another one is this combination of the ARC modules and drivers. So the observation here is that also developers matter as an important context of the code, and learning about the developers can give you also interesting insights on the project and can help you identify the experts you need to talk to, for instance, when you want to implement a new feature. In the interest of time, I can show this also as an interactive demo, but maybe I can leave this also for you in the break and or later if we have more time. What I would be interested now to kind of conclude this first section, this first chapter of the talk, before the break, is your opinion on those 4 different approaches. So these are research prototypes, so we have tested them to some extent, but they are not used in everyday life of the developers already. But maybe you have some ideas on which are the most promising visualization approaches that can be used in everyday work of developers. So which one you would be interested in using when you work as a software developer? So we can start here a little poll in Big Blue Button. I think that should work with this ABC. So we need 4 options. And you can now vote for your preferred option. Votes still getting in. Okay, so no votes are coming anymore. I hope you can see now the results. So we have the winner seems to be C. So maybe the two people voting for C. Can you summarize briefly why you picked this? That would be interesting to learn. Oh, you cannot see the results. So somehow they... Okay, so also the results are gone for me, but they were pretty simple. So B got 1 vote, C got 2 votes, and D got 1 vote. Yeah, so C got 2 votes, so the most votes. So maybe you can comment why you picked this. That would be interesting. See some people typing. The least cluttered, yeah, that's an important point. And that's also what I realized through yeah, then the other comment is also the cleanest solution. That's actually what I also realized, that for maybe the whole field of software visualization, it started with kind of simple visualizations and get more and more complex because the data got more and more complex. And also my visualizations kind of got more and more complex. I think this is still useful, but it might also limit the audience to kind of few experts who are willing to learn to use the visualization and learn to read it in the sense that, okay, what are typical patterns that you can observe? It's maybe not as very straightforward. If you want to have a visualization that many people use, often the visualization should be very simple. But at the same time, you still need to show non-trivial data. So it's really a challenge to find those simple but still powerful visualizations. And yeah, hopefully this approach in C, we made a good compromise here, or found a good solution that is clean and simple on the one hand, and on the other hand shows the right information at the right time and place. And that's always the challenge in visualization, to come up with these solutions. It's easy to come up with very complex ones. I think if you have a complex one, and if it's also a very powerful one, then it's also a good visualization, but not many people might be willing to use it, or at least not if you just use it on an occasional basis. Okay, thank you for this feedback. I think we've spent 45 minutes already, correct? And it's time for a 15 minutes break or something?
Yes, exactly. That's time for our coffee break. I'm going to stop the recording, to pause the recording now.
Okay, so we would come back here at the previous chapter. Again, here the overview of the 4 different visualization approaches, and maybe you can iterate the initial questions. So what questions you can answer with data from software evolution. So this is, of course, not a comprehensive list of things you can do, but gives maybe different ideas what you can do. One is, with data from software evolution, you can see how the system, the history of the system, and get an explanation why the system is currently structured at a low level, so in A, or in the high level in B, like this at the moment. So often to understand a certain thing, you need to understand its historic development. Otherwise, you don't find the right explanations for it. So for instance, if you want to extend a system and you want to know where to put a certain new feature in the modularization, you might need to understand what was the history of this specific part of the software system, why it is like this at the moment. If you just look at the current state, you might not be able to understand this. It can also help use data from software evolution to work on a daily basis with the code. So for instance, you can see which were the more recent changes. So for instance, that might potentially have introduced a bug, or what are the methods that are often changed together that could help you also change the right places in the code. Or you can look at the developers who worked on different parts of the system to identify the right experts you need to ask. For instance, if you want to extend a certain feature, you can see who worked most in this area and in what time range, for instance. Okay, like I said, unfortunately, we don't have time to go into the demo, but if you want to try it out, SetStreams is available online, so the last system, and you can play around with it online. Now let's come to the second chapter, the execution of software. So basically the life of an individual of the species or the software system. Here, you can look at different things. So you study basically the running system. And there you can observe different things. You can observe the change of the memory. So the system manipulates basically the running program manipulates the memory, and finally also the result of the whole system, of the whole computation is reflected in the memory and its intermediate states. And you can visualize this information, that's the left side. Or you can look at the code and the instructions of the code that get executed, and you can visualize how these instructions get executed. So more from the perspective of the instructions. Again, I have here the question, what are the relevant questions that software developers can answer with the data that stems from the execution of the software? And maybe like here, we can kind of postpone this question and iterate over this at the end of the chapter, comparing the different approaches. So again, there are many approaches that visualize the execution of software systems. A specific branch of this is performance visualization. So visualizing how efficient a program runs is, of course, a very relevant question. And there are lots of different approaches covering also different cases like parallel programs and programs running on supercomputers, but also aspects like caches and cache misses and so on and so forth. So there are very different aspects of performance, and the article I'm referencing here gives a nice overview of all these different approaches. Again, here I want to showcase some approaches from my own work. The first one relates back to the very first approach I presented here, where it showed the evolution of the call dependencies in the software system. And you can use basically the same visualization also to show the execution of calls during the execution of the system. So here now the different columns are not different versions of the software, but different phases in the execution of the system. And the dependencies are those are visualized basically that got activated in a certain time frame. And again, we show here the density. And here are excerpts from an execution of JHotDraw, which is a small drawing application, where you can see very different patterns. So very sparse one, like this one here. This might be something like just the system waiting for some input until the mouse moves. A bit denser patterns where you have like very simple things like mouse move, processing mouse move interactions, or then very complex patterns that appear if you actually draw something in the software, for instance. So this is an excerpt, like I said, from a bigger timeline, so a very long timeline like this one here, just cutouts from this. And you need to scroll, or we also developed an adaptive animation approach that guides you through the execution of a system through a lot of different time steps and different patterns. But even scrolling through this very long timeline, quickly you directly observe these repeating patterns or some outliers that indicate some special events. And this can be helpful, of course, for debugging the system and seeing if you execute a certain series of events, what happens in the software system, also to understand the different features of the system. The observation here is visualizing changing execution data is challenging because we get very large scale data. So, and it varies quite a bit with respect to the different time steps. So in contrast to the evolution, where we have like little changes, usually from one version to the other, sometimes bigger, but often like incremental changes, here this dynamic behavior can be very different from 1 second to the next, or even from 1 millisecond to the next millisecond. And as we're talking about milliseconds, and you get a lot of data even if you record the software for only a few seconds of execution. So the scale is much bigger, especially with respect to the timeline. Also here, we try to take this perspective of the code editor and include some of this information in the code editor at the position where the developers actually might need it when they try to understand a problem with respect to the execution, here a performance problem. So again, you see here the declaration and definition of a method, and we see some visualizations attached to it. So this is an excerpt from the code editor, and a bit larger, we see different information encoded in this small glyph here that is behind the method declaration. We see encoded what time the execution of this method consumed. So that's the percentage value here. So it's 0.5% of the total runtime in that case. We see the number of callers and callees of the method. So this one got multiple callers and multiple callees, as well as the self time. So there you can differentiate between the time spent in the method until the method was completed and the time that actually was spent by this method and not forwarded basically to other methods. So, and the fraction of this the self time here marked in this gray box. We get also some information on the threads that access this method encoded in these boxes here. And then we have, for every method call inside the method, a small bar chart that indicates how much of the total runtime was spent with respect to the specific call. These don't add up to 100% in case of recursive calls, because there the situation is a bit more complex. If you don't have recursive calls, these values plus the self time would be 100%, or this overall percentage value encoded in the box here. So here we see the code, that the code is actually necessary to understand the performance information. If you just have user profiling software, you get also like a list of the hot methods, the methods that spend most of the runtime. But then you need to always switch back to the code to understand if this is really an issue or just the regular behavior. So you need the source code, and here we try to integrate both the performance information as well as the source code, and because you need both to understand the performance information and identify specific performance problems and find solutions for them. Another thing is to generally understand the execution of the system. We've seen at the beginning a very kind of an overview visualization of the whole system, so a very holistic view that can be helpful in some cases. In other cases, you have already a very specific focus as a developer. You're wondering, what does this snippet of code actually does? And here we picked methods as an abstraction level. And as a developer can now ask the question, okay, I have a method here. What does this method do in a specific execution? It's basically asking for a documentation of the method, but not a general one, but a specific one for a specific execution. So you can execute the system with respect to specific parameters and then observe what a method actually did in this execution. Like I said, a bit like in the first visualization, but now just focused on one method. And maybe relating back to this discussion of a clean and simple solution, we try to come up here with a kind of self-explanatory, simple solution that every developer can understand without any additional training. So we give here a textual summary of what the method does. So for instance, that this paint entries method was recursively called, and what was the recursion depth, and further information on this. And also report on the method call, so that it called itself as it's a recursive call, so it's a direct recursion. It was only invoked once by another method, which is the paint method. And then you can see also some information about more information about the method calls. And finally, there is a section on the time consumption. So basically the performance information, also embedding some of the information that you have seen in the previous approach as well. So here really the focus is that everybody can understand this type of visualization and textual reporting in this case. So here the observation is that natural language text can explain and help better understand or comprehend complex runtime data. So summarizing this chapter, I like to hear also your opinion first, and then we can discuss a bit why you think certain approaches are most promising, and also go back to this initial question of what questions you can answer with data from the execution of software systems. So first, the question for you, the poll. I start a new poll. 3 options this time. Which visualization approach do you consider most promising? Okay. Great. We already have 5 answers, so I try to publish them, but not sure. So the system says you should see it, but I'm not sure you do. Anyways, all preferred approach B. So 5 times approach B was selected. Okay, you don't see it. Sorry for that. That seems to somehow be a bug in Big Blue Button, really. Anyway, so I could see them, so 5 times B. So why did you pick B? Is it, again, because it looked most cleanest, but then why not C? So maybe you can comment a bit in the chat. C is not code, yeah. I will comment on this also later. Two people are still typing, so I'm waiting for their replies. So yeah, so that is, basically B addresses a very specific practical problem. So it's probably easiest to see it in application, while for A and C, it's a bit broader. And like I said at the beginning, visualization systems usually help to deal with different analysis questions. But still, among the visualization systems, you have those that focus on narrow questions like B, or those that are pretty open for different applications like A and maybe also C a bit. While C is a bit, the natural language text also focuses a lot more. Textual descriptions are not, they sometimes allow different interpretations, and of course you don't have to read it all, but just can selectively read it. But still, it's very specific regarding the questions you can answer from the text, while the visualizations are more open. Okay, and it's nice to hear that B is also not too difficult to understand. It doesn't have these explanations like C has, but like was pointed out, maybe not too difficult to understand and learn to use it. Plus, I didn't show that there are also tooltips, and if you hover something there, you can get more information and also more explanation what the small visualization shows you. So in essence, it's hopefully also quite self-explanatory. So let's come back then to this question of what questions you can answer with these systems. So first, A maybe points to very general understanding what happens during an execution. So for instance, if you're new to systems or don't understand at all what happens, for instance, in case of a certain bug or when using a certain feature, which part of the system get activated and play a role in this, A could be very helpful. If you're new developer for the system, or as an outsider, you want to make a suggestion for a bug fix, this can be helpful to just roughly locate the area where you need to look at, for instance, reproducing a bug, or get a general understanding, okay, what, like, is this module actually relevant when I'm using this feature of the system, or is it a different one? So very general questions like these. B obviously relates to finding performance issues and reflecting on the performance of the system. There are things often like performance bugs. These are performance problems that are basically simple to fix, so that they are not so. Sometimes the performance is spanned for a good reason because it's a hard problem, and coming up with an efficient solution is difficult, but often it's stupid things. Give you one example. Once I was wondering why is the visualization taking so long for showing the picture, and then I realized I just unintentionally called the whole paint method 2 times. It was just doing everything twice. Just delete one line of code and the bug was solved. But yeah, stupid things like this you can actually solve with these kind of visualizations. And C is again a bit more open. It's a bit like a documentation. Documentation helps to understand the system in general, but it often plays a role for solving a specific task, but various tasks doesn't give you the answer for a specific question already. I think I have a bit of time to briefly demo one of the approaches. So C is actually available online, so that's why I pick this one here, C. Let me switch to this and also comment on the code thing. You should be able to see the whole thing now. Two things I want to show here is that even if we produce these natural language descriptions, which are, by the way, text templates, sometimes very complex text templates, so there are a lot of different cases that you need to cover here that can happen. It's nice, but often you want to, see the details of what 66 times means 100%. Okay, this is simple, but in some cases you can, it makes sense to show further details. Like, okay, here 4 methods were mentioned. So what are those 4 methods? You can click on it and then explore the details. It's very standard for visualization tool to provide these details on demand. It's not such common for textual representations. There might be hyperlinks, but not more. That you can actually interact with the text is a bit unusual, but we think it makes sense to some extent to also interact with this. So yeah, I think I opened the wrong one. Let's see. There's a second one. Paint entries. That's the one I had on the slides. So this is the recursive case, and there are other diagrams. For instance, this recursion depth diagram, which is a bit unusual one. So if you have a recursive method, it's basically like a tree structure that the recursion builds. And there you have different levels and different depth. And you can see, like, here we just count for every level how many calls we had. And this is a quite unusual pattern that we have. It's growing first, then going back and forth and back and forth between low and high values. This might be surprising. I think here it's not a bug, but like strange patterns like these could always point to certain bugs in the system. Here, I think it just related to the kind of data we loaded into the system. But it could also point, if you see such unexpected behavior, could point to bugs or could clarify an important misconception that you had before on the system. I also want to comment on that the code is missing here. It's there, but it's not integrated. So we also show the code here that you can enlarge on demand. But yes, it's not as integrated. It would be interesting how to integrate all this information into the code. The challenge there is, of course, you don't want to overload the code editor with stuff. So there's always if you add these visualizations to the code editor, there's always the risk to overload this. But what I learned using software visualization, or in the area of software visualization in general, the code should be always only one click away. So if you cannot go back to the code, there's a high risk that you completely misinterpret the data. So you might speculate, you start speculate about, okay, why a certain dependency is there. If it's hard to go back to the code, of course, you can look up the name and then open the IDE and search for the respective code in the IDE, but you probably don't do it if it's not just one click. And then you start interpreting the data without double checking with the code. And that relates, I think, to software visualization in general, but also to maybe even the whole course you currently take. If you do some data analysis in the area of software engineering, please also go back to the raw data, and often the raw data is the code, and double check with the code if your interpretation that you're currently following actually makes sense and it's not misinterpreting the data. Yeah. So you can try out the whole system, but yeah, it's a prototype. So for instance, what is missing that you can't, you can click on other methods and then see the reports of other methods. That should be, of course, included in a final version of the system. Okay, let's go back to the slides now and see how we can combine the two aspects. How we can visualize the evolution and execution of software and why this might make sense. So we've seen those two time dimensions already. So that's what is called here software dynamics. aspect of software dynamics is the execution, the changing code entities, and the other is the execution. But these two timelines are very different, or two time dimensions. The evolution refers to hours or years of software development, and the data that you can visualize here are the code changes, the commits, the developers, or even the issues from an issue tracker like bugs, bug reports, and so on. And then we have the execution, and here we talk about milliseconds to minutes. So quite different time scale, much more fine-grained. And the data we can visualize here are the call graphs or object graphs that refer more to the program state, the performance, or the memory of the memory usage of the system. So also very different data. Now it's interesting to connect the two, because if you observe something in the execution of the system, you might find the cause in the evolution of the system. So, for instance, a side effect that was unintentionally introduced by a code change. Somebody implemented something new and then introduced, by chance, a side effect that was not wanted, not intended. And you will observe then that in the execution of the system, maybe a failed test case if you're lucky and have a good test coverage. Maybe you will find that out only after the release when a user reports a bug. Or the other way around, if you want to implement a certain change in the system, you can ask what impact will that have on the execution, for instance, the performance of the system. So these two time dimensions somehow interact. And now the question is, how can we visualize these interactions? The very first approach for a special use case that we developed is this approach here. This is this bit simplified illustrating picture here, but you can in the paper you can find the final implementation and screenshots of this also. But here it's maybe a bit simpler to explain with this picture. It shows the execution of stored procedures in a data warehouse. Data warehouses aggregate large chunks of data and for analysis purposes. So they are not the databases that are used in the operations, but more show the whole history of the data. And those stored procedures are used usually to aggregate the data in regular intervals. So for instance, every night, in that case, it was aggregating the data that was collected during the day in another database. And they had similar routines that were executed every week and every month. And then the data warehouse stored this partly aggregated data for analysis purposes. The interesting thing here was we worked together with a company that had records of execution of these stored procedures over years. So I think it was almost a decade of data that they collected. So these stored procedures are a bit like methods that are executed on this database systems, and every time you can record how long the execution took. So we had a long history of this data, so we can now relate the history of the data, of the executions, with the current executions. So this visualization shows only the latest or a selected execution of the system, of the stored procedures, but relates that to the history. So from the history, we know if the execution this time was early or late. So here, in general, the whole process ended late. Although at the beginning it started early, and there are some things that are still on time, but here you see like a chain of stored procedures that got later and later, and this finally caused the problem and led to the late completion of the process. Then you can click on certain things and you can see the details of the stored procedures, as well as the histogram of like how late this stored procedure was executed. So basically relating the current single execution to kind of a history of the executions here helps you identify certain problems. For instance, with this chain of stored procedures and probably the data that was processed in this sequence here. Maybe something was much more complex than usual, or there's some hardware problem with some databases that were used here. So history provides an additional context for interpreting performance information. So not only for implementing changes in the system, you can go back at the history, but also if you talk about execution, it's interesting to study the history of executions. Another aspect that relates or connects performance with the history of a software systems are performance regressions. Here you have the evolution of the code, and you execute the same benchmark always with different versions of the code. And then you might observe that the system gets slower and slower. When you add more features, often these have additional checks, side effects, that even tasks that you did before, that were quick before, get slower and slower. So we're not talking about the execution of new features, but the old features actually get slower because the system gets heavier and heavier. And this is called a performance regression. And for talking about these performance regressions, you need to show different context information. To understand these problems, you need to consider different things. So first, you need to have the structure of the system in general to understand the system. Then you might want to see the dynamic calls that were made in the system at the execution. You need to see the details of the specific execution, as well as the code changes that were made between one version and the other. So very different information that we all want to include in one visualization approach, and that's the solution we came up with. And it shows like some of the previous approaches, the different versions in different columns here. So we have here an XML parser in 4 different versions. The structure is shown here in the rows, also a bit similar to some of the previous approaches. So here you have certain packages that you can extend to class level and even to method level. And then you can see the performance information in the different versions. The big rectangle here is the performance information. The bigger, the worse, basically. So the more runtime it consumes. And the small rectangle here refers to the actual code changes. And if you hover these small rectangles, you can also see more details on the specific changes that were made. And then if you, for instance, spot that between version 1.15 and 1.16, there was a performance regression. So basically, the overall runtime decreased. It's also indicated by this slightly reddish color here of the rectangle. And then you can try to explore and find out the details where the big differences actually happened. That's somewhere here. And also see some additional method calls that were introduced here in blue. So this is cut a little here. In the next version, there's another regression where we can directly see the root cause of the performance regression, some new method calls that were added and new methods that are now used that weren't there before, and decrease the runtime with respect to the benchmark. So the observation is here that diverse context is actually necessary to comprehend the performance regression. It's not just the performance information, and it's not just the code, but you also need to have the history of the code and the history of executions that is relevant here. Finally, basically a bit on Outlook, what else you can do here is you can also take one of the previous performance visualizations, like the things that we added to the code that you liked actually, and extend this in the direction, okay, this showed a specific execution of the system for a specific version of the code. How can we now interact with this thing if we change the code, then execute the software again. In the current version of the system, there's no specific support for this, so you have to remember what was the value before, how it changed. So visualizing there the changes in performance would be helpful, or even predicting the changes. It would be super cool if you add a method call and then the system warns you, okay, this might be an expensive method call that you want to do here. So maybe learning from the history of the specific software system can also help you identify and warn developers very early when they add certain features, how expensive they might be. So this is more just an idea than a specific approach. But the observation is here that interactively changing a system and exploring the predicted effects of changes would be a very desirable thing. To conclude, I want to discuss a few challenges that we've seen in all the 3 sections. So first, that changes are an important aspect. Changes in the code. What happened is the question. What happened in the past is often important to understand the current situation, the current challenges that you face in a software system. Might be with respect to the general modelization of the system, or a specific bug, or the performance of the system. And it might be cool to have visualizations or general software development tools that let you play through some what-if scenarios. What if I do this change? What effect would this have? There are only very limited tools and research prototypes that address this, but I think that can be something that would be very, very interesting to study in the future to support these what-if analyses. We've seen that you need, for solving a specific problem, you need to have certain context. I mean, with a standard IDE, you can always look at the code, but this is often not sufficient. You need to relate the code to some data from the evolution or execution of the system, and vice versa. This data, you need to link it back to the code or to other information like the developers that were involved in this, or you need to link information from the software evolution with information from the execution. So when you develop such tools, it's often important to identify the context that is specifically important for a certain problem. And then the challenge is how to integrate the different analysis, the different data sources and analysis methods in a single tool, that it doesn't get overloaded and cluttered. And in general, yeah, the goal is comprehension and of the code, of course, but also the tool you have should be easy to comprehend for the software developers. So it's nice to have a rich analysis and a rich visualization, but if it's too complex to understand, people wouldn't use it. So the presentation makes a big difference. So if it's understandable and self-explanatory. That brings me to the final slide, iterating over this metaphor. We've discussed the software evolution, but also the individual execution of the software systems here in the metaphor, the life of the individuals, and the combinations of both. And the challenges we see here are how to represent change, what is the important context that you need for solving a specific problem, and how to make the visual representation then understandable and self-explanatory. That's what I've prepared. If you have questions now, I'm happy to answer them. Otherwise, I have also a slightly related tool demo also for some of the challenges I just discussed, if we have more time. Any questions, comments?
Well, maybe I can ask one question. So when you are looking at the palette of visualization techniques you have been discussing, on the one hand, and on the other hand, at least when I'm looking at the daily practice of software developers in companies I know a little bit and in open source projects, it seems that they're not very, how should I put it, they're not really embracing those visualization techniques. Do you see a major transfer challenge here?
Yes and no, to both parts of the question. So I would agree that in some areas visualization approaches are not used a lot. In some areas of software development, they are actually used a lot and embraced, I think. So let me give you an example. In performance, if we talk about performance issues, I think most of the software developers would use some profiling system software, and almost all of the profiling systems come with quite nice visualizations, or some of them have nice, others maybe not so good ones. But for instance, if you look at web development and the performance tools and performance visualizations included in the browsers, they are really rich visualizations, and I think they are used and embraced by the developers. But that is quite different for the different problems. For performance issues, I think visualization is used a lot, but for software evolution, maybe not so much. So there the question is why not? And I assume that the integration in the tools is lacking, and people don't want to use an extra tool if not really necessary. So for performance, it's kind of clear that you need to use an extra tool, and it provides you already with a visualization. Then you as a developer also use it. In other cases, it's basically developers use what is there and useful. But maybe for software evolution, there are some visualizations that are used a lot. For instance, some simple visualizations in the Git timeline. But beyond that, we don't see this a lot. And I think it's mostly about tool availability. And in some cases, but yeah, you're right, there might be some transfer efforts. So it's not just about building a nice tool, but also about better integrating it with existing tools, and that it might not be super easy to do this. And that's what we wanted to explore, especially in the visualizations that integrate with the code. And actually a nice thing that we learned basically while publishing this performance visualization approach that integrates with the code, Microsoft was integrating very similar features in their IDEs to show basically the performance of every line of code inside the code editor. So yeah, as soon as these tools are available, they will be used, I think. And for performance, we've already seen this.
Okay, thank you very, very much, Fabian. I guess that if some of the participants have further questions, they can contact you via email or via Twitter. Both of those are on the slide right now.
Yes.
Thank you again for this lecture. As usual, the recording will be available pretty much immediately on Canvas, and we will also put it on YouTube on the channel of our course. We are not going to have a lecture next Tuesday, but on Thursday we will have the final lecture of the course, which will be the voice of the industry, represented by Dr. Michaela Keiler, who got her PhD several years ago in Delft. And she is working on analyzing code reviews and understanding code reviews and improving code reviews. So thank you again, Fabian. Thank you, everybody, for joining our lecture today. I'm going to stop the recording now. Goodbye, and see you next Thursday.
Goodbye.